Great. Okay, well, welcome everybody to the penultimate day of the summer school. Very excited to have Misha give lecture number 4 in his course. I wonder what we're going to learn today.
Thank you, Boris, and good morning, everyone. Great to be here on this penultimate day. So let's pick it up where we stopped last time, which was a discussion of linear regression. We derived formula for linear, we discussed formula for linear regression, and we saw how the kernel machines actually fit into the framework, although very, very quickly. And I think it's important to point out is that really linear regression or kernel regression with square laws have been extremely informative in trying to understand what is going on in deep learning. Now, many phenomena that we observe in deep learning, although not all, can be usefully thought in terms of linear regression. So it's still a question whether it describes everything that we see, and probably not everything, but well, okay, the question is, of course, it's not everything, because they're obviously, technically speaking, deep learning are not linear, right? Even if in some limits they're linear and so on, but they're clearly not linear in parameters. But the point is that can it explain what is going on? And the jury is still out on that. But what it is definitely true is that it gives us a lot of insight into what's going on. And one thing I would like to point out is a very cool thing about, in particular, Gaussian kernel, is that Gaussian kernel interpolates, which is not the same sense of interpolation that I've been using, between one nearest neighbor and linear regression. So if you take a Gaussian kernel in high dimension and you take a very, very narrow width of the kernel, that it's essentially one nearest neighbor classified. So you can prove it in the limit of width going to 0, it actually becomes one nearest neighbor classified for classification. For very wide kernel, on the other hand, you can prove that it actually becomes linear regression. I'm sweeping something under the carpet. To be really equivalent, you need to assume that that all of my data on a sphere, so they all have the same norm. But yeah, so for very narrow, it's one nearest neighbor. For very wide, it's linear regression. So that a pretty neat aspect of the Gaussian kernel machine in particular. Okay, so let me now quickly talk about, why is it not? Yeah, okay, good. Random Fourier features, which you have already seen, probably in several classes. The idea is the following, that if you have a radial kernel, such as a Gaussian kernel, it can be written as a Fourier transform of a non-negative function, or really measure p. So k of x minus y is equal to integral with respect to p of w, and p of w is some measure of e to the minus 2 pi w x minus y dw, right? And now here is a cool idea originally introduced by Rahim in React in their paper in 2007. They can say, well, okay, instead, if I want to approximate the kernel, I don't have to compute this integral. Actually, this integral itself can be viewed as a feature map. But never mind. Let's just sample from the probability distribution P of w. And if you sample from this probability distribution by some sort of Monte Carlo type of approximation, you can approximate x minus w. And what does a sample of the thing look like? You just need to get a bunch of points wi sample from P of w. And here, of course, I need to assume that P of w is a valid probability measure, so I need to scale it So it's integrates to 1. So here is what we get. We get integral of P of W, this thing, which is just the kernel itself, is approximately equal to sum, or rather average, of e to the minus 2pi wj x minus y. And of course, exponential is multiplicative, so I could write it in this form. And then what you realize, that this is just a feature map. That if I construct feature map like this, that this is nothing else but x transpose in that space. By,
up to a normalization, Misha, you're like 1 over square root of k times that, maybe. Maybe you define
I
the.
I think it's 1 over k here. Oh,
no,
you
I
mean
mean
the feature map itself? Yeah. In this case, I think it doesn't matter because what we're going to do, we're going to do linear regression on top of that. So whatever the coefficient is. But yeah, correct normalization would be 1. So let me see. So the norm, yeah, I think you're right. It's 1 over square root of k to make sure it's normalized correctly. But if you do linear regression on top of this, you will get the same result. It's, we'll scale this normalization. Okay, so yeah, so that is what the feature map is. And now random Fourier network is just basically a neural. It's kind of, you can view it as a somewhat unusual neural network. If you don't like complex exponential, you can think of sines and cosines. Just write it as sines and cosines. It becomes a neural network. In any case, it's pretty similar to the one I described before with ReLUs, but I like this for 2 reasons. First, it's a very neat idea of how to set this up originally. And second, at least for me, this was kind of key to understanding that's what we were actually looking at when we noted this interesting behavior, which double descent. So the key property of this, if you do linear regression on top of that feature map, you get nothing else but a Gaussian kernel machine. And the Gaussian kernel machine is exactly the thing I described last time. So it's an alternative way to approximately construct this map. And the interesting thing, actually, in the original paper, they suggested it as a way to compute the kernel cheaper, because you can do an approximation with hopefully, to construct a kernel machine, you need to invert this big kernel matrix, which is n by n, but you can do it cheaper by, potentially do it cheaper by having the number of random Fourier features, which is smaller than n, smaller than the number of data points. In any case, so here is the key observation. And the key observation, at least for me, was the following, and it's represented by this graph. This is MNIST 10,000 data points. And on the x-axis, I have the number of random Fourier features times 10,000. On the y-axis, it's just 0, 1 loss on the top and in test, and square loss for the training at the bottom. And what you see is the following, that it has this interesting behavior, that it goes through a U-curve up to 10,000. And at 10,000, it peaks. And notice that 88%, this is a 10 class problem, 10 handwritten digits. So 88% is essentially random. So there is essentially no signal there. But what's very interesting is that when you pass this 10,000, your 0, 1 loss, your classification loss, the same happens with the square loss as well. I didn't show it here. It goes down, and actually it goes down quite low, and it goes down to a number which is about 2%, actually very decent. It's an easy data set, but 2% is quite okay. And it's below the bottom of this U-shaped curve. So this is very striking, because you can kind of see this behavior that once the number of parameters actually exceeds the number of data points, in this case 10,000, you get behavior which becomes better. And there is a very clear peak, and this peak corresponds exactly to the point where there are 10,000 parameters, and the square loss becomes exactly 0, because at 10,000 data points, the matrix inversion gives you 0 exact fit. So that was a key observation. And I'll just quickly go over somehow the way of thinking about this. Any questions about this?
Yeah, actually, quick question. So how did you train this model? So if it's on MNIST, are the labels, you're treating the labels as like a number 0 through 9, but treating that as a real number and then doing linear regression, or?
Yeah, so it's one hot embedding. So actually you can kind of think that you're doing 10 regression problem. So actually, okay, when I'm saying the number of parameters is 10,000, it's actually not 10,000, 10,000 times the number of classes. But if you think about it as a tool, it's essentially it's equivalent actually to solving 10 two-class problem, one against all.
Okay.
But it's the same thing, because you need to fit every one of them exactly. So everything scales by the number of classes. So two classes you have just.
Sorry, just to clarify, the RFF is corresponding to the random Fourier nets, like training the neural net. Okay.
Yeah, it's exactly this. I'm training. Okay, I should be more explicit about this. I'm taking the exactly Rahimi-Rek formulation and just trading this alpha I, alpha j, and that is exactly linear regression problem in the feature map. Okay, a wj here I've chosen at random from a normal distribution to make this whole. So you can check that to get the Gaussian kernels, your distribution P needs to be Gaussian as well. It's a calculation. But when you convolve a Fourier transform of a Gaussian as a Gaussian, but with a width which is inverse. So that's basically. I'm skipping over these details pretty quickly because in the interest of time, but also I presume that you have seen these things in some form in other talks. Okay. So now what is going on? So first, it's I mean, at least when I saw this for the first time, that was very striking for several reasons. First, you have this very unusual and very, very clean shape. And this shape you actually see very nicely with random Fourier features. It's very clean curve. Second thing is what is interesting here is that when you increase the number of parameters well below what is necessary for interpolation, what is strictly necessary for interpolation, right? Your result gets better, and it actually gets quite good at the limit. And how good it is? Well, it's about 2%. And this black line here, of course, is a solution to the original kernel machine. And what we know from mathematics is that when the number of features goes to infinity, you actually approximate the kernel machine. And that's exactly what you see here with 60,000 features. You are really close. So everything mathematically, so the math kind of works out properly. Now, another thing which is interesting, it kind of goes against the original intuition of Rahimi and Rek, because they suggested this as a way to compute the kernel cheaper. But you can see that you can only compute it cheaper in this regime when it's underparameterized, because the computation cost is the number of features. You need to invert a matrix whose size is the number of features. And it only is better if the number of features is smaller than the number of trading point, because if the number of features is larger, you can just as well ignore the actual kernel matrix. But the best result you get when the number of features is actually significantly larger than the number of trading points. Although you could argue that this point is still pretty good, and you could get, far fewer features. Okay, so now what is the mechanism? And the mechanism is the following. It becomes pretty clear once you start thinking about it. And the key here is to write the norm of the solution. So you write the norm in the parameter space. And from this computation, the norm is approximation of the RKHS norm. And what the kernel machine does, it actually finds a minimum norm solution in the RKHS norm. So when you look at the norm, which is the bottom panel of this, you see quite a remarkable thing. So initially, every extra feature leads to increase of the norm. But once you pass the interpolation threshold, is what we call this, every feature actually decreases the norm. Why is this happening? And the point is that when you're in underparameterized regime, extra features allow you to fit better. So when you add extra features, everything changes so you can fit your training data better. And of course, the norm in general has to go up because, well, that's what is required to fit the data. However, in the overparameterized regime, you don't need to work hard to fit the data better. You already have solutions which fit the data exactly. So when you add a feature, that actually expands your zero set, the set that allow the set of solutions which fit data exactly. And within that set, because it's bigger now, you can find solutions of smaller norm because that's what you're looking for. So the more features you have, the smaller the norm of the solution is going to be. In the limit, as we know again from math, it converges to the kernel machine. That's exactly what we see. So that's a mechanism. More solutions give you more flexibility to find a good solution. And Sidek, I see that you have a question.
Yeah, I just have a minor question on the previous slide. It's just about some details. So if you go on the previous slide, the two images, or yeah, exactly. So over here you have 10,000 points, and each of the point has 10 classes, 10 targets. So 10 to the power 5 things to interpolate. But on the bottom figure, you have 10 into 10 to the power 3 features. So 10 to the power 4 features. I'm a bit confused now. You said the interpolation threshold is at kn, but over here kn is 10 times bigger than features.
No. So the number of random Fourier features. Yeah. So think about it. The fact that it's 10 class key is irrelevant because you're kind of solving each problem separately. Just think about it as solving each problem. So you have 10 prediction problem, but you're kind of solving each one of them separately. So don't worry that it's a 10 class problem. Just think about it as a 2 class problem. And everything matches.
Okay, so the interpolation threshold is just at n number of features.
So at the bottom, actually, it's not 10,000. It's that many features what I have in the bottom here for every problem that you are solving.
Okay.
So really, you should multiply it by 10, but you're kind of solving in the same way. Actually, the kernel is the same. Okay. I think it's confusing. Maybe I should just give it a two-class problem. Then you would.
Well, the reason is because I've also been reading the paper, and there was another experiment where you actually train the network, like MNIST, where you train neuron by neuron. Over there, the interpolation threshold is slightly different. In one case, I noticed it is d equal to n. In the other case, it is d equal to kn. Maybe I didn't misread the paper, so it could very well be the case, but that's why I was confused.
So in general, the number of parameters need to be equal to the number of classes times the number of data points, right? Because for each class, so think when you do one-hot encoding, right? For each class, you have 1 degree of freedom for each class, right? So if you fit 10 classes, you need 10 times as many parameters. So I think it matches in the paper, but I will have to look at specifically.
Okay, thanks.
What we say there. Varun?
In the next slide where you're talking about the norm, this norm is just computed as like the normal like L2 norm in whatever dimensional space of the parameters that we have, but then you're saying that it approaches like this sort of theoretical RKHS some Hilbert space norm that we might not have an access to of what the actual, like in this case, when we know what the kernel is, then we might be able to figure out exactly what the Hilbert space inner product is. But it's just like you're saying that, oh, it's as we get bigger and bigger, it's going to approach the Hilbert space inner product.
Correct. So this is a norm just for linear regression. So you do the feature map and then you compute the norm of the predicted that feature space. So
Gotcha.
in that sense, it's just a linear norm. But what we do know is that at the limit at infinity, the solution that norm actually match the kernel space. So in this case, we can compute both of them explicitly, and that's why we know that they're close.
Gotcha.
But of course, in principle, we may have feature norms for which the kernel we don't know how to compute.
Cool. Thanks.
Hassan, question?
Yes, so I think you passed across this point last time, but just making sure, what's the reason that the solution of the kernel machine goes to the minimum norm once you are in the over-parameterized regime?
That's how I solve it, right? Because the machine is, when I do the machine, which is matrix inversion. So when I write my solution, sum alpha I k of xi, and I put dot here, and I solve for alphas to fit the data. That actually is the minimum norm solution in that space. So this is the magic of kernel machine. Because in principle, to solve something with a minimum norm in a functional space, good luck with that. But in this case, because of the representative theorem, instead of doing this, I just solve this linear combination, and inside of the linear combination is a number of data points, so it's not really difficult to solve it at all. So we can think of kernel machine as this wonderful computational tool which converts this infinite dimensional problem to finite dimensional. Because of matrix transpose, somehow you can solve it. It's the same problem as for linear regression, right? You can solve it in size D or you can solve it in size N. But here, G is infinite, but N is finite. Navid?
Hi, Professor. So I had a question, maybe a little bit off topic, but like, what would happen if you regularize with norm? Would you observe this test error behavior again?
Yeah, you would observe. So it depends on how much you regularize. So the more you regularize, the more you bring down. So if you regularize a lot, maybe you can remove. You will not have the sharp peak, but you would get something very, very similar. So you might not get this peak. You might get something smooth here, but the norm would still. Okay, it depends on the amount of your regularization, because if you very heavily regularize by the norm, you can bring it down, make it very flat here. Your solution will probably also get worse than perform the test error. So
I see, thank you.
If you regularize too much. If you regularize lightly, you'll still get similar. Yeah, so this is a minimum norm solution, actually. I have it right here. And this is the kind of upshot, is that more features give better approximation to minimum norm solution. Okay, so now let me make one point very quickly about connection to one nearest neighbor. And actually, the interesting thing is that there is one nearest neighbor on this graph if you choose the kernel correctly. So just choose the kernel to be quite narrow. And we know that for a narrow kernel, Gaussian kernel machine implements one nearest neighbor. You can check this as an exercise. It's a nice thing to check. So what is happening here, that of course, if I do appropriate random Fourier features for the Gaussian kernel, which actually sampling from a distribution with the opposite covariance matrix. So because a Fourier transform of a Gaussian switches the covariance. So if in one dimension, if your variance was 5, it will become 1/5 for the sample. And then of course, using a lot of the random Fourier features, you will converge to the kernel, and that will be one nearest neighbor. So you can write one nearest neighbor classifier as a feature map, which is nice. Okay, so now there have been quite a lot of sort of empirical analysis of this, or empirical observations, which showed similar behaviors, not just for linear regression type of methods, but for other things as well, including neural networks, and or even things like boosting. And sort of the summary of this was represented as this double descent curve, which kind of postulated this as a phenomenon, as a sort of alternative, or as an expansion, I should say, for the classical U-shaped curve. And what's happening is that in the underparameterized regime, you have the U-shaped curve, but once you passed over the interpolation threshold, your performance generally decreases. There are some questions, you know, can it do something like this? Yes, it can. So it doesn't always decrease monotonically there, but it seems that in most practical cases, it actually does. And it seems that very large models typically is quite good in terms of performance, even when you just fit it exactly without worrying too much about, you know, doing like early stopping or regularization. So couple of points. So first, the classical curve ends at the interpolation threshold. So that's another very nice thing about interpolation, which you cannot really see when you add regularization as an extra term, is that when interpolation starts, you get a sharp peak and a clean separation between classical and modern regimes. And the second thing, which is, you know, very, very consistent with the practice of deep learning, is that large models perform well. And as we have seen, very often, if you just take a model here, it's better than the best model at the bottom. Again, this is not always true. And in, you know, with toy examples, you can construct examples. With synthetic examples, you can construct examples which go either way. So it really depends on the data and on the exact model. But in practice, it seems that frequently this is the case. Perhaps this is the case because this model is actually just very difficult. So there may be that great classical type of model which we are not finding because of optimization and other issues. Gati, question?
Right. So there's, I guess, two. So you kind of answered one of them. Is like, is it monotonically decreasing after the interpolation threshold? And you're saying, okay, so in most cases it is. So I wonder if there's any kind of criterion for determining that. And also, like, the second question would be, even if it is monotonically decreasing, is the global minimum to the right or to the left of the interpolation threshold?
So we don't know. I mean, I think that's the biggest. So there are two questions here. In practice, it seems to be monotonically decreasing. I don't want to say always, but typically, I would say. Whether it's lower or higher, that's perhaps the main thing which is missing for the theory, because if we had a very clean criterion for this, we would have a full alternative to the classical optic theory. We would say, okay, here is a way to, you know, see whether the classical method is better, or, you know, this modern interpolation type of model is better. We have this for specific models, but we don't have a very general criterion, sort of analogous to optic theory. And I think for the future, that would be the biggest thing to develop, to have a full theory of this, which takes account of it. In practice, just from a purely practical point of view, from what deep learning people do, they just take a big model and they don't worry too much about it. And it seems that big models always give you better performance. Again, when I say always, it's not technically true, but it's a consistent pattern.
So for instance, again, I know of like empirical evidence of where for CNNs, it seems that there is kind of an optimal number of channels, which is not infinite. Further than the test performance decreases. So I guess that's one instance of where it seems to be like what your purple curve there. There's some kind of optimal complexity.
You know, yeah, that could be one, but even for CNNs, I've seen different stories about them, and certainly in some cases, infinite do seem to work quite well. So it's, I would say it's unclear, right? So there may be cases where it's infinite is strictly better, and maybe cases when finite gives you something a little better.
And but are there any like hints towards? Yeah.
Yeah,
Okay, so
I
there
don't know.
any
I don't
hints
know.
towards
Yeah.
this theory? No. Okay, it's hard.
I kind of feel that taking infinite is fine if we're doing things right, but maybe we're not doing things quite right, because especially with neural networks, there's just so many parameters. It's like it's impossible to understand. So, but take it with a grain of salt. You know, if I knew like a strictly better method than all neural network, okay, yeah, you know, I would be shouting it at every corner, but I don't. But it does seem that infinite work quite well.
Do you mind if I make a very brief remark, Misha?
Of course.
So maybe just as a partial answer to your question, Gadi, you know, I think to understand when the behavior is non-monotonic to the right of the interpolation threshold, it makes sense to ask why is there a peak at the interpolation threshold itself? And it's, at least for these kind of linear models, it's basically some matrix is very poorly conditioned, or more precisely, the smallest eigenvalue, you know, is very, very close to zero. So, you know, you can imagine that the other peaks happen where one mechanism to generate them is similar. You have some kernel, which is a sum of kernels, and, you know, they become ill-conditioned at different complexities of the model, that kind of thing. But it's not clear that that is what drives non-monotonicity when you do see it in practice.
Yeah,
Right,
so that's an excellent, if I just follow up on Boris's point. So one way to set up the peaks is exactly this. So you can construct this artificial examples, but you have clustered data with clusters of different sizes. And if you play with the parameters, you can create these peaks because you kind of first fit the first cluster, and then you have some function space like a sum of this, which fits the second cluster, gets a peak there, and so on. So you can create these peaks, and there are other mechanisms for creating peaks as well. When it happens in practice, it doesn't seem to be happening. At least we don't really observe it. I don't know of sort of very clean observations of this.
So there's this like NIPS paper from last year by Giulio Biroli and company, where they explicitly call it like triple descent. And then the peaks, the other peak, Boris, is at, you know, one is that interpolation where, and the other is where it equals the width equals one is for the dimension and one is for the number of parameters, and they call it like linear peak and nonlinear peak. So I wonder which other matrix is poorly conditioned there, or to put the.
Yeah, maybe we should take this offline because it's a separate discussion. But in some sense, I kind of feel that, you know, we've done a lot of these experiments and we just don't see a lot of these peaks, although you could construct these peaks.
Okay.
But so I don't know.
Okay, thank you.
I think peak is actually not the most interesting aspect of this. The cool thing about the peak is that it separates these regimes very clearly. And maybe in their paper, it kind of serves the same purpose. There are different regimes which are being separated. But the peak itself is not super interesting. What is interesting, to me at least, is that the big models perform. The peak somehow is visually very nice. It separates stuff. But conceptually, as Boris said, it's just the fact that some eigenvalue becomes small. To think about it, when you invert a matrix, if this matrix is square, it's actually the worst case, because when you have many more parameters, you have many ways to choose the smallest norm, right? So you have many ways to fit. And the one with the smallest norm will actually be kind of nicely conditioned. But if you only have one solution, that's the solution you're committed to, and it fully depends on every noise that you have in the data. So in some sense, what they teach us in linear algebra, how to invert square matrices, is the worst case. It's the least stable case. So you really should teach us how to invert, you know, very thin, or very tall, or very wide matrices. It's much better, mathematically much more stable, much better condition. But in any case, I should continue. So there have been a lot of work about this recently. You've seen some of it in various classes and other discussions. And I think the kind of upshot is that really linear models provide us a lot of insight, and we can understand a lot of things, and we can analyze them quite specifically in some cases. And one thing I would like to actually highlight is that recently it was shown the deep neural network effect of arbitrary depth with ReLUs are equivalent in the limit to Laplace reproducing kernel Hilbert spaces, which is a very cool connection. So you can actually say mathematically that infinitely wide ReLU network of arbitrary depth is the same functional space as Laplace kernel. I'm emphasizing it's not the same kernel because different kernels can give you the same spaces. So you have to equivalent spaces.
Wait, are you saying the norm is the same as well, Misha? I think you're just saying it's a vector space of functions.
No, the spaces. So its functional space is the same.
Yeah.
But the norm is the same, but the norm is equivalent, so it's bounded. Whatever.
I see.
The norm of one spaces is sandwiched between. So norm space 1 is smaller than alpha norm space 2 and bigger than beta the norm space 2 for some alpha and beta. So the space is the same. The norms are somehow equivalent, but they're not the same. And you can actually see how it can happen. Okay, it's a slight aside, but think about, suppose you have a perturbation of your kernel, which is finite rank, for those of you that will be the equivalent kernel, the equivalent space, because you're only doing a finite space perturbation. But the kernel will be actually quite different. So in practice, it's a little bit tricky because this finite perturbation of the kernel, finite rank perturbation of the kernel could have a big difference to what you do in practice. But still, it's very cool. So the space is the same. It's really nice. Okay, but let me not talk about the linear case much more. So maybe I'll just summarize it. This is kind of the summary for the linear. For the classical empirical risk minimization, we're trying to minimize the loss over the training data. In this modern interpolation regime, it's more useful to think that we're minimizing the norm under the fitting conditions. And the cool thing is that if you do SGD, then the norm minimization is somehow hidden within the dynamics of SGD or GD. And in fact, you can solve first and second problem by GD. You don't even know whether you're in the over-parameterized or under-parameterized regime unless you somehow look at it. So these two things look superficially very similar from the dynamic of SGD or GD, but they actually have different properties, as we have seen. In one, you're kind of in the one side of this curve with one, and the other side of the curve for another one. Now, another way to increase smooth is if you could do averaging. This is not the same as minimizing the norm, but remarkably, it looks quite interesting and sort of similar. And remember that picture that I have with overfitting, when I take the number of random features was kind of small compared to the number, a little bigger than the number of data points, but only a little bit bigger. So you get this very spiky curve. But if you take a bunch of these very spiky curves and you average them, you get this red curve. And this curve is very similar, although it's not quite the same, to what you get when you increase the number of random Fourier features, or random ReLU features. So you see, when you have a lot of random ReLU features, the randomness is always not visible. So 20 draws, so for 3,000 random Fourier features, the variance is very small. When you have a small number of random ReLU features, 35, then the variance is quite large. But when you average, the results are pretty comparable. Mathematically, they're not the same. And you can kind of think that the left looks, if you know what bagging and boosting is, that may remind you of bagging, the left part of this, and the right part is kind of like boosting. Actually, this is an interesting thing because this relates to an algorithm which was proposed by Cutler and Zhao 20 years ago, called PERT, Perfect Ensembles of Random Trees. I think that's what it stands for. What you do, you build a random tree which fits your data exactly. Then you build another random tree which fits your data exactly. And you build like, 100 random trees which fit your data exactly by doing random splits. And then you average them. Now, this is not the same as bagging, but it has a lot of similarity to bagging and really, really looks like what I had here in this one. It's essentially the same procedure. Turns out it works just as well as bagging. And although it was never a very popular algorithm, I guess because it was kind of weird because you want to. So notice that an average of interpolating classifiers is also interpolating. So so I guess it was kind of a weird procedure, and it wasn't clear why it's better than bagging. It was similar. But in any case, it was surprisingly that's an interpolating algorithm from 20 years ago. What is, I think, remarkable is that averaging interpolating trees is actually better than any individual tree. So really, this variance reduction really does help. And we've done some experiments which are shown on this graph. On the left, you can see that, oh, maybe I don't want to describe this in detail, but basically you do the same thing. You can first grow the tree, and when you grow individual tree, you kind of go this U-shaped curve, because a very big tree, which fits the data exactly, is actually not that good. But once you start averaging them, you immediately get better results, and this kind of corresponds to this tree. So increasing complexity by just growing tree, you get this U-shaped curve. But increasing complexity by averaging is great. So here is a summary, and here is the sort of framework, the way at least I've been thinking about this. And you think about this as an Occam's razor based on the inductive bias. And what is Occam's razor, right? Occam's razor in the classical form is something like do not multiply entities beyond necessity. Basically, you want to choose the simplest explanation for your data, right? So reformulating it in a more modern way. So what you want to, so if you think about it, choose the simplest explanation which is consistent with data. And you see, interpolation is actually the very basic notion of consistency with data. So what you can think is the following: choose the simplest function which fits the data exactly. And what is simplest? Well, maybe it's a smaller function, or the kind of general way to think about it is some sort of smoothness maximization. You can still get spiky solutions because that comes from fitting the data. But among all the solutions, you should choose one which is smoothest. And that's sort of the premise. And then you can say, okay, well, there are several different ways you can minimize, you can maximize smoothness. First, you can look for this, as we discussed, minimum functional norm solutions like kernel machines, or approximate with RFF and ReLU features. You can do it implicitly by some sort of optimization, which is known to increase smoothness, to choose solutions with maximum smoothness or close to maximum smoothness. Or you can do it by averaging. You can start with solutions which are not smooth, but fit the data, and you just average a bunch of them. And you know that the average of this magic of averaging, right? Averaging makes things more smooth. It's actually kind of remarkable if you think about it. So when you average a bunch of very spiky things, right, you get something much nicer and much smoother. Right? You average a bunch of random walks, which are like super spiky, right? And you get something like a normal distribution. Okay, so that's interestingly, all of the things coincide for kernel machines. So that's another reason to think that kernel machines are somewhat special, because you can solve them explicitly, you can solve them implicitly. Averaging corresponds to this Gaussian process point of view on the curve. So that's maybe the framework you may one might consider as a. So you want to maximize smoothness, but where is the smoothness coming from? Well, in some sense, the smoothness comes from nature. Is that why can you make this assumption that fitting the smoothness data, fitting data by the smoothest thing is good? It's because we know that in some cases that the edge is smooth. And what does it mean? When we flip one pixel of an image, the label of this pixel does not change. When you move a sensor a little bit, the reading of the sensor shouldn't change very much. one more point here is that you can think of that you can all think as a kind of hierarchy. So the smoothness hierarchy of this norm hierarchy is something that we come with, right? It's our prior, our bias, our idea. But fitting the data kind of takes precedence. So the first point is that, okay, data is God-given. I'm just going to fit data. I'm not going to worry about noise and so on. But among solutions that fit the data exactly, I will choose the one which I think is best. So you can view it as a regularization with an epsilon, with a very, very tiny infinitesimal regularizer. So I have this huge space of solution. Among those, I will choose the one which is best. And Yona, you have a question.
Yeah, this is actually from a while back, if that's okay. Back when you were talking about way back how deep neural networks like approximated the Laplace reproducing kernel Hilbert space, I assumed it was as width went to infinity, but I wasn't sure. Was that
Correct.
like
Correct.
as just the width goes to infinity, or is it like in the sense of Roberts and Yaida, where like the like width to depth stays constant and they both go to infinity?
So I don't know what, yeah, so I'm not sure what happens. I think their result is fixed depth, but arbitrary. So arbitrary depth, width goes to infinity. I don't know whether we can prove this in some, whether there is some ratio. I'm not sure. But you can take a look at their papers. Okay. I don't think they had a result like that. As far as I can tell. Okay, so, oh yeah, and I should point out there is some very interesting recent work in that by Bubek and Selke, who showed that smoothness may actually require overparametrization. Maybe it's necessary to have overparametrization. Okay, so let me somehow maybe just very quickly summarize that. And I want to start with optimization because somehow optimization is getting from more and more to the last talk. So this is a landscape from this point of view, from the double descent point of view, the landscape of generalization. You have on the left, to the left of the interpolation threshold, you have this U-shaped curve. To the right of the interpolation threshold, you have this modern interpolation where the choice of the solution is based on deductive bias. And now we have some analysis, at least for linear and kernel, we're starting to understand this. I think one point I would like to make is that overfitting in this, it still exists, but it's not something which is obviously related to the training loss at all, because the training loss can be relatively large, or it can be relatively small, or it could be identically zero, and you can still overfit. So overfit relates to some sort of interplay between the model and the parameters, but it's not anything obvious. Like, you know, you cannot say that when the loss on the train set is small, you overfit. So another way to say about it, if you have an overfitted model, there are two ways to regularize. One way is a sort of classical way to regularize by reducing the number of parameters, but you can also regularize by increasing the number of parameters. And both may produce similar results. And so that's I think a new thing that doesn't exist with statistics or machine learning. Kalen, question?
Yeah, so when you talk about smoothness of the function, we saw in one of the earlier lectures how there was these, it was basically linear, and then there's these spiky points that fit directly to the data. Whereas in this other example just before, we saw the bagging, which was an analogy for the functional smoothness, and we saw that it actually was smooth. So I was wondering, in terms of neural networks, does it converge more to a generally smooth function, or actually one that's smooth and then super spiky and then back to linear?
So think about Laplace kernel, right? So we know that neural network in some sense equivalent. No, so I don't want to say Laplace kernel because it's the same RKHS, but not the same kernel. But if you, it's maybe okay to about it. They implement something similar to Laplace kernel. Laplace kernel is that. That's actually kind of spiky, right? You have this discontinuities at the peak. It's not as extremely spiky as the ones I had, but it's fairly spiky. What is more, I think, is those pictures are slightly misleading because they're one in one dimension. And what happens in high dimension is that things which are less spiky in one dimension, like Gaussians, become more spiky in high dimension. Because somehow in one dimension, Gaussian looks pretty smooth, but in high dimension, there are more directions. It's more peaked, right? Because it's peaked like that in every direction. So I think there is some sort of subtle interplay with dimensionality, which those pictures are not capturing. So I wouldn't be surprised, that I haven't thought about this, but I wouldn't be surprised even for those trees, when you average them at high dimension, you get fairly spiky things like simplex-like structures. Like simplexes, a triangle in one dimension doesn't look so spiky, but a triangle, a pyramid, like in D dimension, is extremely spiky because that area is very, very tiny, close. 1/2 to the D. So that must be happening for neural networks when they apply it in high dimension. So high dimensional neural network and low dimensional neural network, you have to be a little bit careful because they may be implementing the same kind of function space, but they not necessarily have the same spikiness. Okay, but because I would like to switch to optimization and at least start saying a few words about optimization today. Okay, in any case, you can ask questions if you would like after the class is over. So this has so far been generalization. Now, remember there was a second question, and in some sense, it is a more tractable question. It's an easier question. And the question is simply the following: why is SGD so successful in optimizing highly nonlinear neural network? And that for a while, I don't think it's such a puzzle anymore, but certainly for a while, it had been a big puzzle because, well, think about what it is. It's like traditional view is that tractable optimization is essentially convexity, you know. And the reason for this is actually, you know, if you look at the landscape, which is something like, you know, imagine like this. If it's a highly non-convex landscape, right, then locally you have convexity in each of the things. So if you do a gradient descent type method, right, so the way to think about it geometrically is just you have a ball and you just roll it downhill with some friction. You see where it stops. And of course, if you roll a ball here, it will stop somewhere here. If you roll it here, it will stop there, and so on. We know this. So gradient descent will converge, but it will only converge to a local local minimum. So local convexity means, or convexity means that, like, convexity is the way to analyze it. And we can only hope that it's local because, well, there is really no way this neural network can be globally convex. It's kind of obvious. So that's a traditional view. And it turns out that this reliance on convexity, and I strongly believe that we really need to rethink this very systematically, because convexity is simply not the right notion to think about optimization of these regimes. And I am certainly not arguing that convexity is a bad idea. Convexity on its own has this beautiful mathematical structure, convex analysis, you know, convex geometry, and all this wonderful things related to convexity. But if we want to study optimization by methods like gradient descent, we really should not look at convexity, at least in overparameterized settings. And first, let's just set it up a little bit. So as we discussed before, once you somehow look at machine learning abstractly, right? This is simply solving a system of nonlinear equations. We simply want f of w if I think about optimization, right? So when I think about generalization, so think about it. Generalization and optimization are kind of dual to each other. Generalization, I look at X, right? And I want to say what happens to X's, which I haven't seen in the past. For optimization, I'm looking at W. I'm fixing my axis, and I just want to find W such that it fits my training data. So if you kind of suppress your dependence on X, you can think of this as solving a non-linear system of equation f of W equals Y. And for linear regression, this is simply a linear system of equations. And of course, solving f of W equals Y is equivalent to minimizing the square loss, f of W minus Y squared, okay? This is simple enough. Now, so that's a kind of loss function that I have in mind. And I hope I will have time next time to give some comments about the square loss versus other losses. We'll see. Okay, so what does this mean? This means that if I'm under-parameterized, I don't have enough parameters to solve the system of equation exactly. And the best I can do is to find some local minimum of this function. And of course, you don't expect any convexity, but what you do have, you have this isolated local minima. Again, generically it's isolated. Of course, you can have examples where they're not. And locally around this point, you have convexity. Why? Because it's some sort of generic problem. This is a generic problem. Well, what happens when you over-parameterize? When you over-parameterize, you have many solutions, right? Which give you zero. So you don't have one global minimum, you have a manifold of global minimum which solve your system. So the global minimum of the loss function are solutions to the equation, the parameters which fit my data exactly. So for the linear case, it's just a line. Now, I have manifolds of global minimum. And once you look at this picture, the picture on the right, you realize that this picture is actually completely incompatible with convexity. So this is what one may call essential non-convexity. And what does it mean? If that there is no way such a picture can be convex, even locally. And let me say no way. Let me make it a little bit more explicit here. So no way, by no way, I mean the following. So suppose the manifold of solutions is not linear. Okay, that's the only thing. I find to be precise. That's the only thing that I'm assuming. Then it has some curvature. And let's think about one-dimensional case. You could do think about one-dimensional case. Suppose it's not a line. Then the thing has a curvature, right? So suppose in this small neighborhood of a single point, I have curvature. Then this cannot be convex. Why? Because the set of global minima is actually, if that function is locally convex, then the minima of a convex function is also a convex set. Okay? So minima of a convex function for a convex set. So if my loss function is locally convex, then the set must be locally convex. But the only way a set can be locally convex, a one-dimensional set, if it has no curvature, if it's a line. So unless every point here, every interval, every segment of this curve is exactly a line segment, this cannot be convex. So the only way you can have convexity if you literally have a line. And in fact, in high dimension, it has to be a convex set, convex subset of a low dimensional alpha plane, which is obviously very, very special. So you can write a more specific mathematical condition, but this gives you a complete idea of this. And you can actually see, and maybe this is one thing I would like to show, how to think about this. To think why this condition, the convexity condition, is super fragile. Just think about a cylinder, okay? So suppose I have a cylinder. A cylinder is something like this, right? can imagine I'm just slicing it forward. So this is my graph of a function. So if I select the lines of the plane, the set of global minima is this line. So this is convex. But now imagine that I'm twisting the cylinder a little bit, like a car tire, like half of a tire. I'm just twisting it just a little bit. Even if I twist it very, very tiny bit, the convexity is broken. So convexity is super fragile. It doesn't even hold under the tiniest perturbations. And you can think why this is happening. It's because one way to think about it more analytically. So geometrically, it's because you're introducing curvature to the set of minima. Analytically, it's because you can see that when you're twisting it, there will actually be negative eigenvalues on the hash chart there. It's easy to see with this causes. So that doesn't work. On the other hand, think about gradient descent in this picture. If I have a ball here and I let it go, right, the ball will actually happily roll down to the bottom of the valley. So from the gradient descent point of view, there is really no difference at all between the straight cylinder, the cylinder which is slightly twisted, like a car tire. So that's an upshot. Is that basically convexity is just not the right way to think about success of gradient descent. And it turns out that we do have, I'm out of time now, but we do have an alternative to this. So it cannot be based on local convexity, but we have actually a classical alternative to this, something called PL condition from Polyak-Lysevich. In fact, Polyak in 1963 showed that this condition implies convergence of gradient descent. And I'll discuss this next time. But if you just want one message about optimization for now, is that instead of convexity in overparameterized cases, we have to think about PL condition. And that actually resolves a lot of issues and produces a very clean. And I'll stop here and I'll take questions. And I see there are several questions. Varun?
Hey, so if you go back to the previous slide where you were talking about the ball rolling down this explains, like, obviously that we can interpolate this is I guess I'm like wondering if is this like the curve that you have, is this like the empirical risk curve or like the general, because the reason I ask is even if you get to the global minima of the empirical risk curve, with this picture, I'm not able to see or like intuitively see that the norm, like the RKHS norm will be minimized, like the interpolated norm would also go down using this like picture.
Very good. There is no interpolated, there is no norm here, right? This is so this is okay. This is a nice way to view it like this because it separates things. It's not complete. I'll talk about this. And this is actually points at the biggest gap we have because we don't have a complete match between this view of optimization and what is happening in generalization. But in some cases we do it. I'll talk about neural tangent kernel when we actually do it. But this is just optimization for now. So there is no norm. You just want to minimize. You just want to solve a system of equations, right?
Gotcha.
That's what, we're in the pure math mode, right? We just want to solve the system.
Sounds good. Yeah, thanks.
Yeah, next. I don't know who was next.
Hi, Professor Belkin. I have a question. So do you assume something of the manifold when you prove that the landscape cannot be locally convex? The next slide. Yeah. Do you assume something of the manifold, like how the manifold looks like and all, when you prove this? Yeah.
It's almost nothing. So basically, as long as there is some non-convexity, you can think about it as a curvature of a turbo. You can think there is an analytic way also the equivalent. Basically, as long as there is some, essentially, as long as there is a manifold of solutions, it's very difficult for the function to be convex. It's almost impossible for the function to be convex because you have to have some very special condition of the Hessian Or equivalently, you have to have this condition that there is no curvature. If you just write an arbitrary system of equations with, say, neural networks, it's not going to satisfy. So if you take a realistic neural network, the set of solutions is never going to be convex even long. Oh, okay, I have to be a little bit careful because if it's a ReLU, it will be piecewise. It will be piecewise linear. But it's still not going to be convex, but it may be like if you have a piecewise local solution, maybe it will be convex. But yeah, essentially, I think the useful way to think about it is just not going to be convex.
Okay. No, the thing that's really interesting is local convex. Like you cannot say that it's even locally convex. So just which might require some stringent conditions on the manifold itself, right? If you are saying that it cannot even be locally convex.
It's very difficult for it even to be convex at a point. It requires some very special. You know, think about a system of equation of degree 2, okay? Suppose you have a quadratic equation, right? Can quadratic equation have only one root? Yes, it can. X squared equals 0 has only one root. That can happen. Or you can say it's a double root, but doesn't matter. But it's a special condition, right? If you choose coefficients ax squared plus bx plus c, you can have 0 roots, you can have 2 roots, but having one root is very special. So this is analogous to that. You would have to choose something very special for this to happen. It's exactly.
Okay, that sounds right. Thank you.
Next, Yona. Oh,
okay. Yeah. My question is just from the same picture. Is there, like, it's obviously like it's shown in the picture, but is there some reason in this framework that we think there's no other local minima? Because like there could be sort of, to my mind, like disconnected local minima still that just like one of them is the global minimum that's this manifold. So is there some reason for that?
Yeah, so you see, if you think about, there are more parameters. So what's a global minimum? A global minimum when you actually have some W for which you cannot make f of W to be equal to 0. And around that point, you only get it worse. So it's possible, but again, it's a very special condition because you have more parameters than equations. So typically, if you have some sort of general position condition, there is a way to make it smaller. There is always a way to make it smaller because there are somehow a lot of directions that allow you to go down. Can you have a local minimum? Yes. Is it generic? No, because basically if you change the equation a little bit, it's like, again, having a double root for a quadratic equation. It can happen, but if you change the equation a little bit, it disappears. Same thing happens here. Of course, 0 is special because this is a norm, right? The norm cannot be smaller than 0. The way it's written, you cannot go below 0. So yeah, so essentially from every W, you should be able to somehow get down to 0. And usually gradient descent, again, usually gradient descent will do something like that.
Makes sense, thanks.
Mm-hmm. I see Mufan.
I have a similar question on this topic. So is it possible that we're looking at the weight spaces sort of leading to this non-convexity that we're seeing here? Is it possible that we can try to solve for a different metric, like Riemannian metric, such that it ends up being convex?
Not very difficult to imagine. So yeah, so the question is there some other notion of convexity which helps here? Any notion of convexity, you see, I don't know any notion of convexity where the set, I think the set of minimizers of a convex function is convex in, I think, under any notion of reasonable convexity. So you would have to have some notion of convexity where the set of minimizers is not convex. I don't know if it exists. But you see, the problem is convexity is very fragile because if you just twist something a little bit, which is convex, usually that breaks convexity. The way to think about it more analytically is that if you take a composition of convex functions, they're not convex because you have to check the second derivative. I'll talk about this next time. But the second derivative is not a product of derivative. So first derivative is a product. You have the chain rule. So the second derivative, it's a sum of things. And one of the sum you control, the other sum you have no, the other term in the sum, you have no idea what it is. So that's kind of analytical representation of this fragility of convexity. So I don't think there is any obvious way to deal with this. I actually don't think there is. I actually don't think it's even needed because we'll discuss next time. PL condition is beautiful and it allows you to do essentially everything that you want. There are some caveats, but essentially it's simpler than convexity. So I think convexity, in some sense, I kind of feel that we don't have this PL condition in the underparameterized world, or at least it's not that interesting in the underparameterized world. And people have traditionally looked at underparameterized setting, and it wasn't clear what PL condition was given extra to convexity. But in the overparameterized world, using convexity is some sort of kickback to this, you know, to the thinking in the other parameter. I don't know, it doesn't make sense, but that's, yeah, maybe I'll. Siddharth, you have a question?
Yeah, so my question is again something similar over here. You were also alluding to conditions on the Hessian required. And my question is, what if the loss landscape is degenerate? So there is a non-trivial null space of the Hessian. Then what happens? Then you could still have some, let's say in that space, of course, you could have some convexity, right?
Oh, yeah. No, null space, the Hessian always have a null space here, right? Just because of the rank.
Right.
So the question is, around this null space, so think about the point on the zero curve, on the minimum curve. At that point, the Hessian is positive semi-definite, but not positive definite. Okay, why is it positive semi-definite? Well, it has to be positive semi-definite because it's a local minimum.
Yeah.
But it cannot be positive definite because the direction along the curve is also local minimum. So it's always positive semi-definite. Now, what does it mean? That means that if you want this to be convex, it better be positive definite around this. So that's a very special condition on the Hessian, because when you move a little bit off the thing, suddenly the zero eigenvalues, the eigenvalues change. And what you're saying is that no negative eigenvalues can appear. Well, why cannot it appear? There is actually no reason that it cannot appear. That's why it's a very special condition. Okay, does it make sense?
Yeah.
That's thinking from a Hessian point of view. I think geometric is a little nicer because you kind of see the curvature, but you can think equivalently about the Hessian. Varun, question?
Yeah, can you go back to the PL condition? I'm trying to see like if our loss landscape sort of if this condition holds for our loss landscape, will we like what kind of geometric intuition can we get? Like, will I get the same type of landscape as in the picture that you're showing? Or it seems like this will give, I like to think more geometrically than not. So I'm wondering like what will I hopefully glean, or is this something for next lecture that you're going to go?
Yeah, I'm going to discuss it. So the argument is essentially when you're sufficiently overparameterized, everything is going to be PL. Oh, okay, I have to be a little careful. Not everything is going to be PL. So okay, let me. So this is kind of preempting the next one. So if this is your parameter space W, then there will be points here when it's not PL. But this point will be very few. So there will be like a low dimensional space of parameters when this is not PL. But a generic point is going to be PL. So again, this is the same thing as for a quadratic equation. Actually, I think, look, you know, this idea of genericity, generic choice of parameters, right? Take a quadratic equation, choose A, B, and C at random. In general, there are 2 roots or 0 roots if you only look at real values, real solutions. There is, however, a special thing when the discriminant is 0. b squared minus 4ac equals 0. It's a actually algebraic subvariety where you will have multiple roots, double roots. And that set is something like this, right? And it has a codimension of whatever, 1. So if you somehow not happen to be close to this, you are fine, essentially. That will be the point. And in general, you're not close. Although for neural network, if you initialize them in 0, it turns out that 0 is bad. And because 0 is actually a saddle point and it's not PL and so on. So there may be interesting regimes which actually happen close to this non-PL setup. But yeah, we will discuss this in much more detail next time. Yeah, Siddharth?
Just a minor question over here. So the neural network initialization should not be there along this line of degeneracy, or is it for it's for the initialization that we are considering, right? In this figure?
True, yes. So yeah, that's exactly right. So basically when you initialize, you have to be away from this bad set.
I see.
And if you choose this at random, so when you use, so for NTK, it's all very nice. It works out nicely, and you can prove that for NTK initialization, you're guaranteed to be far away, and that you could prove convergence and everything. Now, what people do in practice, people do different things, and sometimes maybe they initialize close to 0. So again, this becomes much more subtle once you look at you. But NTK works well in practice, so that I think is another point. NTK solution is fine. Yeah.
I'm asking because I've been working on a similar result on Hessian, and sorry for the background noise. So the result is that at initialization for ReLU neural networks or things like ReLU, the initialization, like the Hessian at initialization is degenerate. Like this, the Hessian in the sense of like the NTK would be degenerate essentially for like at initialization.
So ReLU is very tricky.
ReLU or leaky ReLU, all the activations functions will satisfy that the activation function is the derivative times the argument.
You see what bothers me about ReLU. So it may be, so I don't know, I would have to think how it compares. You see, the ReLUs or anything which has this kind of linear structure, it's very peculiar because the derivative is actually 0, the second derivative is 0, right? But it's a delta function at some point. So it's hard to put it in the same frame. That's why I like smooth activation functions, because you're guaranteed that second derivatives exist and so on. When you do ReLUs, you have to look what happens when this ReLUs becomes very large. And then you somehow, to get some sort of idea of the Hessian, you have to average this delta functions over some sort of path. And I think it can be done, but it's a different. It's just much trickier than using differentiability. So I don't know how exactly this PL condition map onto the ReLU, I guess.
Okay, I see.
So, but yeah, but I think it would be interesting to understand what is the connection. But it's not so straightforward because your second derivative is infinite, right? So
yeah,
you have to somehow average infinity. It's like dealing with Dirac delta functions.
Okay, cool. Thanks.
Sorry, I maybe didn't understand something right there at the end, but isn't the PL condition you formulated only a first order thing?
Well, so yeah, in this case, yeah, so actually that's a good point. So just to check PL condition, it's the first order. But to get the scaling, I'll discuss this next time. You see, the problem is, how do you prove that PL condition holds? You don't. I mean, you have to look at the tangent kernel, and then you have to prove the tangent kernel doesn't change. If that's the way you want to prove it, you have to look at the second derivative. The tangent kernel is the first derivative, but that's where the second derivative comes and bites you. What I think is true is much broader than this. Actually, so the hypothesis is that you probably don't need anything to know very much. So hypothesis is that essentially take a general nonlinear system. As long as it's sufficiently overparameterized, it will be PL. You don't need to know anything about tangent kernel and so almost nothing. It should be a very, very general claim. But we don't have the tools to prove it. So the tools that we use for neural networks have to do with the second derivatives and tangent kernel being constant and so on, or scaling, things like that. And then you need second derivatives. I'll discuss this next time because this is. But yeah, look how beautiful the PL condition is. It's first order. Well, okay, convexity, of course, you can say it's zero order, right? Because you can check it. But zero order is kind of cheating because who can actually check it as a zero order condition, right? The way you check it, you say something about the hash shell. The eigenvalues are positive. But how do you know what eigenvalues of the hash shell are? You don't in general, especially for something like neural network. This condition, you just need to know something about the gradient. That's a lot easier than the Hessian. And then the neural tangent kernel actually gives you a very powerful tool to check this condition. So this maps exactly into the tangent kernel. Though that will be the discussion next time, how to check this condition, how it maps onto this kernel, and then why constant NTK gives you a tool to prove that basically essentially all wide, well, I don't want to say all, many wide neural networks of almost arbitrary architecture. If you initialize them with NTK, they satisfy PL condition, they converge, GD converges, SGD converges, everything is really quite beautiful.
Thanks, Misha. I had another question about the PL condition. So I think maybe, I'm sure it's very old, but just I saw it first, or this type of thing in like the compressed sensing literature. People used to talk a lot about like restricted strong convexity conditions. Is this like I should probably know this, but is this like similar to that? Or is like one stronger than the other? Do you know? Or is it clear what I'm asking about? I'm sorry.
Yeah. There are several conditions which kind of like this. I think they're slightly different. So I don't remember which. I know exactly the condition you mean, but I don't exactly remember what it is. I think it's not quite the same. I think they're a little different, but I think sort of conceptually speaking, PL condition is more power, is broader. But I think you can have examples which are PL but not strong convexity, and the other way around. What I will argue is that this condition is really the right condition for overparameterized. It's this one. It's not. There is this restricted strong convexity. There is this other thing. There is also something called pointwise convexity, which is also similar to this. But let me maybe make one point about this. Here is a nice thing here, is that, and I'll talk about what's the version of it which we call PL star, which is even simpler, but essentially it doesn't have W. But the nice thing here is that it's only about the loss function itself. It has nothing about actual W star. So that's so you can completely write, you can completely analyze it in terms of loss. That's not so much with convexity itself. Well, kind of. Yeah, I'll discuss this next time. Essentially, with this PL star condition, you basically get rid of this L of W star completely, and then it becomes even simpler, and it looks like this overparameterized system actually also satisfies PL star. But I first want to discuss why we want to get rid of this. I'll leave it for the next time. Any other questions? It's almost time, right?
I just wanted to, the thing that kind of struck me about the PL condition is it looks like somewhat like the opposite of a Lipschitz type thing in some sense, like the derivative is going to be bigger than your change. So like that's what's kind of like puzzling. Like is it meaning like you can take steps and like it's gonna get to where you need to go in some sense. It's like your step that you need to possibly take is like greater than the distance you need to go, I guess. That's how I'm trying to think of it in a geometric way, and that's why hopefully you can elucidate that.
Yeah, no, that's right. We want the derivative to be big enough so the ball can roll, right? If the derivative is small, it will just stay there, right? So and it turns out that this relationship between the loss and the derivative of the loss is exactly what allows the ball to roll. It's very neat. It's yeah. Actually, Pollack really discovered. I mean, it should be really called Pollack's condition because Lysevich used a similar condition, but it was in a different context that he didn't look at credit himself. He wanted to analyze some manifolds, some algebraic varieties. Okay, but I think I should. It's almost 9:30, so yeah.
Okay, well, I'm glad there are so many questions. I think it's really rather fascinating. But yeah, maybe we can take the questions offline. You can message Misha or put it on Slack, or there's also, I should remind everyone, TA sessions later today, so you can ask the TAs, and it's great. Okay, so thanks again very much, Misha. I think Andrea is here now, and when you have a second, Andrea, you can share your screen, but there's still a couple of minutes.
Thank you, Boris. Hello. Thanks, everyone. Hi, Andrea.
Hi, Misha.
Did your student pass the dissertation defense, Andrea?
I would say brilliantly. Okay, I'll share my screen. Hopefully today there is no hiccups. Actually, I figured out what was the problem yesterday. Somehow the network that I was using for some mysterious reason doesn't allow anymore screen share.
Oh, weird.
Okay.
Okay, yeah, maybe we should just wait for 1 or 2 minutes, just in case someone is tuning in at the exact moment.
Sure.
I guess
give people time to breathe.
Yeah, exactly. Maybe before you start, Andrea, let me ask you a general question about your previous lecture.
Yes.
You had lots of results about, sort of kernels that are functions of the Laplacian on the sphere last time, and, things in terms of, implicitly in terms of if you have the right decay of eigenvalues, you can learn various things, okay, so on and so forth. It seems like it's potentially natural to ask whether the same question is true on a manifold. You take a complete closed Riemannian manifold, take the Laplacian, there's well-known spectral theory for it. And you could try to ask whether these kernel methods on the manifold will learn points, point data, if and only if you have the right number of points to interpolate kind of in the similar way as you had. Is that, known? Is that interesting? Is that more or less the same as the techniques you already have?
Okay, so okay, let's put it this way. So the thing that we had there, okay, it's not function of the Laplacian. It's exactly the kernel was a function of the inner product, right?
No, I mean, as an operator, right? The eigenfunctions are the spherical harmonics.
Right, but because it's rotationally invariant now, both the Laplacian and I don't know if there is anything important about Laplacian, right? I mean, the eigenfunctions are the spherical harmonics are eigenfunction of any rotationally invariant operator.
I know, but I'm saying every rotationally invariant operator is a function of the Laplacian. That's like a theory.
Right. Okay.
But okay, sure. Whatever. But you can take any one of them, is what you're saying.
Sure. I mean, because any rotational invariant operator is a function of any other rotational invariant operator. Yes, there is some non-degeneracy of eigenvalues. But okay, that doesn't really matter. I mean, I think that okay. So I would guess the following: that if you take if in this calculation, what we use a lot, for instance, is the fact that the diagonals elements are concentrated. In the case of the sphere, these are always equal to h of 1, right? And we have a generalization when these are concentrated. So if you now want to go to a manifold, probably you want a manifold with a group, right? That acts on this manifold in a transitive way, perhaps, and then you want that perhaps K to make the theory as easy as in the sphere case. Probably you want something like this, right? That the kernel is invariant under actions of this group, right? And so this will imply in particular that the diagonal elements are constant. Now, do I know other examples of manifold that satisfy this condition? Well, one would be the torus, right? So if you take the torus in D dimension, that would satisfy this condition. And okay, I'm sure that that there are many others. Now, I mentioned the general result. So we have a general result that establishes more or less the same picture. And what we need there is basically some condition. The two most important conditions are some condition on this, that all these elements concentrate around their expectation. Max over I. This has to be small. And then another condition, we need to have some hypercontractivity property, right? So for doing this random matrix theory calculation, we use something of the following type, that if you look at, let's say, BL, basically the eigenspace spanned by the top eigenfunctions of K of the kernel, then if you take any function in this eigenspace, this function satisfies hypercontractivity property. So if you raise these to an exponent, I don't know, P, this is comparable to the second moment.
Mm-hmm.
To the P over 2. Okay, so this is satisfied in the case of the sphere, is satisfied because these are polynomials. And the uniform measure of the sphere is hypercontractive or polynomials. The same holds for Gaussians, etc. It's a kind of notion, things that happens, concentration thing that happens naturally in a high dimension. I would think it works also in the sphere. But,
okay, yeah, thanks. That's really useful. I appreciate it.
Okay, so perhaps now we can start. Actually, I wanted to start by showing some figure, at least, since I didn't show any real figures today. This is to show this staircase phenomenon in kernel ridge regression. Okay, so if you look at it, what I'm doing here is here I'm fitting a very simple linear function in 30 dimension. Okay, so it's high dimensional, and I'm doing it with the kernel ridge regression with this type of kernel. And here the form of H is just the form of H that comes from ReLU activation functions. And you see, this is what we plot here. This is from a paper with Theodore and Song. What we plot here is the error of kernel ridge regression for this kernel, and you normalize to be 1 for the trivial estimator, and you see that it goes down at a certain point, and this is, the theory predicts that somehow this should have a kind of threshold phenomenon for large dimension around 1. Okay, so this matches more or less the theory, and if you increase the dimension, one can check that this is the way it behaves. And this is a function that is a quadratic function that has 0 projection onto linear function, and the theory says that it should transition at 2, log n over log d equal 2, and this is a cubic function, and so you see this is what happens here, and the cubic function, see, you are not able to learn it even with n squared samples. Now, in this plot contains something more that I didn't explain. These functions have a specific property. They are translation invariant, right? So if you act on this vector x with a shift, this function do not change. F of gx is equal to f of x. And one can exploit this by constructing a convolutional kernel that averages over the shift. So this is the way it's done. You take just an inner product kernel and you average over the shift. This is just the infinite width limit of certain neural networks, certain convolutional, very simple convolutional neural network. And despite its simplicity, you see a big improvement. In particular, you see an improvement that is roughly a factor d. Okay, so this is a little simulation about kernel, and so I thought of sharing that. And then I wanted to show 2 more figures. One is about the proportional regime. I'll actually show one third figure later in the lecture, but before the lecture, this is about the proportional regime that I didn't touch really in my lecture, in which number of neurons. So this is the random feature model, really. So here, what I'm looking at is this model where I'm fitting only this second layer and first layer fixed, and these are curves of the test error prediction versus the regularization parameter for various value of this parameter. This parameter is the overparameterization, really, so it's n over n. So these are asymptotic curves for this, in this regime for the risk as a function of the regularization in the ridge things. And okay, so these are interesting figures, because they speak to the question that I mentioned, whether interpolation is optimal or not. And we see an interesting phase transition phenomenon here, namely depending on the value of the SNR. These are 2 figures for a different SNR. Lambda equals 0 is optimal or not. So this curve, correspond to various overparameterization with the dashed curve, the black dashed curve corresponding to infinite overparameterization. So you see that infinite overparameterization is always optimal. Okay, and now it's always the lower envelope of this series of curve. And then what we see is that what is the optimal lambda? Well, depends on the SNR. At high SNR, somehow the optimal lambda is at 0. So interpolation is optimal. At high SNR, at low SNR, instead, the optimal lambda is strictly positive. Okay? So in the theorem that I stated, there was not such phase transition because we looked at non-proportional regime that is somehow simpler. In the proportional regime, the picture is kind of more nuanced. So at high SNR, you don't need to regularize. At low SNR, you need. And okay, so this matches our intuition that somehow ISNR applications are better suited for neural network or for deep learning methods. Okay, so what I want to talk about today is somehow closing the loops, and I opted to devote 2 lectures to this, but ended up having less time than I thought. I mean, being slower than I thought. So I want to start. So I want to look at the neural tangent model and look at how finite number of neuron compares to infinite number of neuron, always under the linear regime approximation. And here I'll think actually of 2 separate models, and I give results about 2 separate models. One is the random feature model, and the other is the neural tangent model. And always the W are fixed, and the W, throughout this lecture, I'll take them random. Not normal, but uniform. On the sphere. And I fit B, the coefficient B, just by ridge regression. So either RF and T. Now, as I described the model, really, in the second lecture, I think I should look at the sum of these 2 models and fit both of the parameters. But as you will see from the results, it's quite clear that the sum of the 2 models behaves as the NT-model for generic activation functions. So, looking at the sum is just a matter of, makes things more complicated. And I want to unnecessarily more complicated technically. And I want to look at the RF model because we have slightly different style of results there. Okay, so what we saw that as n goes to infinity, both of these models are equivalent, both behave in the same way. Namely, if you take xi uniform on the sphere of radius square root of d, then if n is smaller than d to the L plus 1 minus delta and bigger than d to the L plus delta for L an integer, then basically what you obtain as a model f lambda is very similar to the projection onto low degree polynomials up to L of f star of the truth. One way to say this in words is that kernel ridge regression is very similar to polynomial regression. Now, the relevance of polynomials, of course, is that they are eigenfunctions of the kernel. And yeah, I mean, in general, for more general data distribution, the generalization will be, regression onto eigenfunctions, top eigenfunction. Okay, so now we want to look at the impact of n less than infinity, how this result, how wide the network has to be to achieve this kernel behavior, infinite kernel behavior. And okay, so here is a theorem about random features. say, it says the following. So assume a similar thing, that is d to the L1 and the number of, so this is for random feature, and n and also here L1 and L2 are integers, and the delta is a positive number, and also we want n over n, and so what this says basically is that lowercase n and uppercase n are well separated. Okay, they are not close to each other. Then call L the minimum of L1 and L2. So of the two exponent, then the risk of random feature regression at lambda f star for any lambda small enough, f star is equal to the projection onto polynomial degree at most L of f star plus smaller order term. Okay, so what does this say? Okay, so the important thing in this statement is that what matters is the minimum of L1 and L2, where L1 and L2 tells me the behavior of the number of neurons and the number of samples. Okay, so in other words, there is two regimes. Regime number one is that n is much smaller. The number of neurons is much more smaller than the samples. This is the underparameterized regime. And the approximation error kinds of dominate in this case. Namely, the error that the risk, the prediction error, or the test error is roughly independent of the number of samples and only dependent on how many neurons you have. And the other case is n much smaller than n, so the sample size much smaller than the number of neurons. So this is the over-parameterized regime. And in this case, the statistical error dominates. Okay. Okay, actually, I want to show you a third figure to illustrate this. And this is this one. So here, what we did is that we took one such network, I mean, many of these. So we took a two-layer network or many of them, and then we trained it in the random feature, we trained it in the random feature way, varying the sample size and the number of, the network size. And you see this completely symmetric picture where, having, this point as roughly the same risk as that point, okay? In other words, okay, you can look at this plot in two different, and okay, there is this regime when, uppercase n is similar to lowercase n, the risk blows up, okay? But, if you if you are away from this boundary, then there is, the risk decreases and, there is complete symmetry. So there is two ways to look at this. Either you fix the sample size and you increase the complexity of the network, the number of parameters. So this is moving along such a line. If you move along such a line, what you see is that as you increase n, the sample size, then you see that the error decreases, and at a certain point saturates. Okay, so here what's happening is that, okay, there is a blow up here, but doesn't matter for us. And so what happens here that you have more and more data, but at a certain point you hit a network, complexity threshold. The network is not rich enough to capture all of your data. And then, the other way you can look at this is you fix okay, I made a mistake. This was, of course, the other type of line. I confused the two axes. So this was moving, fixing the network size and increasing the sample. And the other way is that I fix the sample size and increase the network. You have a given data set, and then you build a bigger and bigger model. And what the theory says is that I will see basically the same plot. But the interpretation now is different. The interpretation is that I have a given data set, I make my network richer and richer, and at a certain point I hit a wall, and the wall means that I don't have enough data to fit a bigger network, so I'm not degrading things, right? And the plot on the right, so what you should do is, if you're free to choose your network size as you want, but you don't want to build it too large, is probably move along such a line like this. So over parameterize somewhat, but not too much. Okay, so these are a few scalings. So somewhere the literature, there was work suggesting that you should have the size to be the square root of the sample size. But according to our theory, this is not what you should do. You should have perhaps the network size, the number parameter, to be a small power, 1.1 plus epsilon power of the sample size. And indeed, this is what works best.
Okay, can I ask a question, Andrea? Sure. So I think it seems kind of intuitively clear that you should have this symmetry between capital N over little n and little n over capital N, or like the role between little L1 and little L2. Do you agree with that statement?
It should be intuitively clear. I mean, yeah, I don't know. I mean, we we discovered this by first looking at the two limit cases, right? And realizing that, I mean, it's not clear to me why should be intuitively clear.
So the way I was thinking about it is, I don't remember which of your L's corresponds to what, but let's say that L1 corresponds to like capital N. Mm-hmm. That fixes kind of the width of the box into which you get to partition your space up. You don't see higher frequency functions.
Right.
And then the other L fixes the spacing between the data points that you actually see. So somehow if you see very few data points on like a very fine grid of boxes, you may as well average the boxes. Because
right.
And vice versa. If you have lots of data points, there's no point in resolving further, and somehow you get to the same size.
Right. I mean, yeah. I mean, this is reasonable intuition.
I'm not saying I can make it into a proof. I'm just sort of wondering if.
Yeah, I mean, it's a reasonable intuition, and indeed, if you write down things, I mean, the way we realized this was really by looking at the two limit cases, right? On one case, we looked at the kernel, so number of neurons infinity and finite sample size, and on the other, we looked at the infinite sample size and finite approximation power, so finite width network. And then you realize quite clearly there that so we discovered that the two were completely analogous, and then we thought a bit, and it's not clear that there is no interplay of the two, right? When both are finite, a priori you could think there is, okay, some strange interplays of the two. But basically, yeah, what you are saying is, right. I mean, what happens in high dimension, somehow the smallest of the two, when one of the two scales like a bigger power of the dimension than the other, then is like sampling at very, very fine grid infinite rate there. So you would not see such a kind of sharp, precise trade-off in finite dimension. Now, I don't know if the symmetry survives in finite dimension, right? It might be that some form of symmetry survives in this model, because there is the additional fact that in this case, really the activation depends in a completely symmetric way on the two, etc. Right? So yeah, so that I don't know, and it might be that for this simple spherical case, things keep being asymmetric in finite dimension. But in general, I mean, we have a version of this theory, again, theorem under the general kind of abstract setting that I described above. And I think that, in general, it will not be completely symmetric in finite dimension.
Yeah, that certainly sounds right. Thanks very much.
Yeah. Any other question? Okay, so this describes the picture in the random feature model. So basically, the infinite width limit is reached as soon as infinite width. So if I take n equal n to the 1.1 or 1 plus epsilon, this is very similar to an infinity. So this is the summary of what we learned from the random feature. And well, in the neural tangent model, basically the same happens, except that the role of n is played by the number of parameters, that is the number of neurons times the dimension. Okay, so this is a theorem now that I state that with Yichao Zhong. And so we have a version in a paper that is on the archive, and a more general version that hopefully will post soon. Again, the setting, okay, we need to make this assumption once more. And so this is that there exists a C, so the style of the result is slightly different, but the content is similar. There exists a constant C such that if nd log nd to the C is bigger than n, then the risk of neural tangent regression at regularization lambda and ground truth f star is equal to the risk of the corresponding kernel ridge regression. This is kernel regression with respect
Andrea,
to...
we can't see your screen.
Oh,
I mean, it's frozen.
Sorry. This is something that happened to me. Okay, so this is the statement. If the sample size is again away from d to an integer, now nd much bigger than n. So think of this. So this is really the key condition. Then you get the risk of kernel ridge regression, where this is kernel ridge regression with respect to the kernel that is the anti-kernel. plus an error that is the scale of f. Okay. So okay, in this factor logarithmic factor are probably an artifact of the true, in particular logarithm to the c. Really, I don't expect, but okay, it's just to make us able to write a proof of this. And so morally, what you have here is that the difference between NT and kernel ridge regression or finite width and infinite width goes down like the square root of the number of parameters of the network divided by the number of samples. Okay, so as soon as you are in the over-parameterized regime, the two starts getting closer. Okay, so this is okay, to the best of my knowledge, is the most accurate result of this type. Is in this case, this is limited to this special spherical distribution.
Sorry, Andrea, so this gets worse and worse as the number of parameters grows.
Sorry, I made a mistake. I flipped the thing, right? Thank you. This is
that sounds like a disaster.
Yeah, it's just a typo. Well, that is what somehow traditional. This is what traditional, wisdom would say, that as the number of parameters gets much larger than the number of samples, things get worse. But okay, so this is the modern thing. So in this case, while the previous result was for, we have generalization for other distribution, in this case, we don't have a generalization for other distribution at the moment. Okay, so let's see how are we doing with time. Yeah, so if, so perhaps let me pause a moment to see if there is questions about this.
Is the difference between this result and the 2021, which I've read several times, that you're doing it for L greater than 1 now, or are there other differences too?
Yeah. Okay. So I should mention there is a paper, as I said, on the archive in which we assume capital N less than a constant, an arbitrary constant times the dimension. In other words, the network looks like this. Networks looks like this. This is D, and then here it it can blow up at most by a constant factor. So the fact that capital N is less than a constant times D tells us what? Tells us that I want ND, for the assumption I want ND much bigger than the sample size. So this means that the sample size is much smaller than D square. And what this means is that basically I can only learn linear function and start to learn quadratic function, perhaps a little bit, but not much. Okay. Instead, here we don't have this assumption anymore. Okay, so we spent the last year trying to remove this assumption, and now we have a written proof that we checked a few times, and we are polishing before putting it out. Okay, and luckily the new proof is simpler than the old, so you're welcome.
Looking forward to it.
Okay, yeah, we are quite happy about that. Okay, so if there is no other question, I want to give some intuition about the results that I mentioned in this lecture, and actually in the previous one, and this kind of behavior when sample size of number of neuron increases. So I'll focus actually on the simplest result. That is the result for kernel ridge regression. Okay, I want just to give an idea of the simplest piece of the basic piece of the proof. But okay, so what is the setting again? We have a kernel K x1 x2 that is a function of the inner product x1 x2 over T. All right, and the most important step is understanding. Okay. The crucial first step is the very first step is understanding the empirical kernel metrics. Okay, so I'll write this as K, perhaps I'll call it K subscript n. So this is a matrix, the n by n matrix that you obtain by evaluating the kernel at the sample points. Okay, and so one fruitful thing is to think of this as a finite n approximation of a stochastic approximation to the kernel operator that I write as K without n. The kernel operator, is an operator, is a compact operator in L2 that we can write as an integral operator. Where mu is, of course, so this is over the sphere, but I stop writing this thing, and this is the uniform measure. Okay, so you can think of it as you are taking this, infinite dimensional operator, this compact infinite dimensional operator in Hilbert space, and you're approximating it with a very big matrix. And now we want to understand how the two are related, right? And in particular, what is the structure of this, the eigenstructure, the eigenvector and eigenvalue structure of the finite approximation. So, of course, an obvious point to start from is to understand the structure of the integral operator. And this, since it is rotationally invariant, is relatively easy. This decomposes into eigenfunctions, eigenspaces that correspond to polynomials, to spherical harmonics. So there is some lambda j of d square, and then pj, where this is a projector onto degree j polynomials. Or spherical harmonic. Okay, so little parenthesis. If I call Vj the space of degree j polynomial, the dimension of Vj called Bdj is of order d to the j, as you might guess, right? The number of degree j polynomial is d to the j, and it's not quite d to the j because there is there is degeneracies because we are looking at it on the sphere. Okay, and okay, another equivalent way to write this is the following. If I look at the kernel evaluated at point x1, x2, so there are a few different ways that it's convenient to move within. One equivalent way to write this decomposition is that if I write the corresponding kernel, this you can write it as a lambda square JD. The reason why this is square is, of course, that case PSD. Okay, so I can always write the eigenvalues as squares. And the reason why it decomposes the eigenspace are spherical harmonics is just rotationally invariant. So you can write this as by taking a base of the spherical harmonics. So let me write it as, and then a base of degree J polynomials, such as the spherical harmonics, and then take the inner product. So here, what is the convention that I use? YLX is a vector of dimension BDL, where each of these are all the spherical harmonics of degree L. And I take them to be normalized to have L2 norm equal 1. So this means that this is the condition that these have to be orthonormal. Now, okay, so I brought now the kernel operator. It's important to understand, the behavior of these eigenvalues, and I claim, okay, so the important claim is that for any fixed J, lambda JD square is some constant psi J square divided d to the L, d to the J, plus small order of d. So for large dimension, these xi's behave like 1 over d to the J. And okay, so one way to do it, to understand, okay, I will not explain how to prove this claim, but one way to, I'll describe at high level the calculation, and you can check it yourself. But one way to understand it is the following. If I look at this representation here of the kernel, you can equivalently write it in terms of what are called Gegenbauer polynomials. I don't remember what is the normalization that I was using, but let's say this one. Okay, there are many, I don't remember what is the standard normalization. So these are Gegenbauer. What is the definition of Gegenbauer polynomial is simply that Qj is a polynomial of degree J, and they are orthonormal with respect to the measure, the distribution of what? Of x times E1, 1 over square root of d, if I follow the same normalization when x is uniform of the sphere of the square root of d. Okay, perhaps I put a square root of d here so that I don't have this trouble. Okay, so it takes a little bit, or it takes reading Wikipedia to see that basically the projection onto degree J polynomials is represented as an integral operator as a Gegenbauer polynomial. One way to define Gegenbauer polynomial is simply that you take among all polynomials of degree D, I mean all the span of spherical harmonics of degree L, you look at the only function that is invariant by rotation around the fixed axis, E1, say, and that is a polynomial in X times E1. Okay, now these are orthonormal with respect to the projection, the measure of a one-dimensional projection of a vector that is uniform on the sphere. And from that, you can understand that the Gegenbauer polynomials for large dimension, let's put here a dimension D, for large dimensions must be very similar to Hermite polynomials. So this is fact number one, the J Hermite polynomial. And fact number two is that, okay, by orthonormality, this implies, the above implies also that lambda JD square, you can write it as integral of K E1 square root of D X times Q E1 X mu dx. And this is equal to integral of h of xe1 over square root of d times q e1x mu dx. Okay, now you know that. So why are close to a Hermite polynomial? Well, because in large dimension, this measure is approximately Gaussian. If you take a vector uniform on sphere and you project it along one coordinate looks approximately Gaussian. So the orthonormal polynomials with respect to the spherical measure must converge to the orthonormal polynomial with respect to the Gaussian measure, which are the Hermite. And then you have this representation of eigenvalues in terms of integrals with respect to Gegenbauer polynomials. And for this, from this, you get basically what you wanted. So, you write it in terms of expectation with respect to the Gaussian measure of something like Hermite of something. And now I got several factors square root of d wrong, but in the end, once you do this calculation, you get d to the minus j. If you get it, do it correctly. Okay, so this is a small detour to explain this claim. This is an interesting exercise in orthogonal polynomials. But once you have that claim, then the intuition is quite clear. Again, what is the form of your kernel? Let me write it. And now I want to sample this, and so I split it in several pieces. So look at the finite kernel matrix, and I assume n much bigger than d to the L and much smaller than d to the L plus 1. And what I want to do is now split this sum, treat differently the terms up to the L and beyond L. So you get this lambda j of d square, and then I put here a factor n, and then what I call psi j transpose, and then the sum of all the other terms, I call it the matrix n bigger than L. Okay, so what if psi j, since this matrix Kn is obtained by evaluating K at the sample point, psi j is the matrix that is as this form. So it's psi j x1, psi j xn. So evaluating the spherical harmonics at the n data point, I put a factor n in front, so I'll put a 1 over square root of n. And this is, of course, a matrix that is R to the n by BDL. So it's a very skinny matrix. Okay, now I claim, it's easy to check that this matrix, or okay, requires a little matrix concentration proof, but this matrix is approximately orthogonal. Right? You can see that in expectation, I mean, this is 1 over n, sum over j 1 to n, and then you have yj sum over l, okay, sum over I, xi, psi j, xi transpose. Okay, so you can imagine that this is very similar. So this is the expectation, is the identity and concentrates around the identity. So this is an approximately orthogonal matrix, and so this is approximate eigenvector decomposition. What happens about the part that is bigger than L? So I'll write it as a diagonal part. That is always the same by rotational invariant times the identity plus an out of diagonal part. And what is the out of diagonal part is the matrix with entries, the high frequency part of the kernel ij, I different from j. So what do you expect? So let me call this piece kappa, I don't know, for lack of better name. And what do you expect about this out of diagonal part? Well, these are high frequency component is a matrix, so they will look like basically random. And so you're looking at n by n matrix with entries that look very much like random. So you expect that the operator norm of this part is of order what? So first of all, okay, you can compute that each of the entries is of order of size 1 over square root of d to the L plus 1 by using y, by using just the expansion of, you write this as an inner product. And you see that all these entries are small and this is a high degree polynomial. So you get it. And so the total norm will be a square root of n factor bigger. If you have a matrix. This is the heuristics that you would have if this matrix had independent entries. The size of each entry, I mean, the operator norm would be square root of n times the size of each entries, and this turns out to be correct. Entries in reality are dependent, so you cannot use this heuristic, but the heuristic is correct. So if I stick everything together, I get what? I get that my kernel matrix is what? Is sum over j okay, let me write 0 to L, and then there is lambda jd square times n times psi j transpose plus some constant times the identity plus a small l. Okay, and so these are approximately ortho. So what I know about the various pieces, I know by what I said before that this is about n times psi j square divided by d to the L. And then what I know is that this is of order 1. And this has operator norm that goes to 0. Okay, So if I neglect, first of all, what do the eigenvalues look like? You see, these xi's are constant. So the first eigenvalue is of order n. So as I go up in J, the top eigenvalue, so J equals 0, 1, 2, up to L. So the top eigenvalue is of order n. The second, you have a group of dimension d of eigenvalue that are of size n over d, and then n over d square, blah, 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 and then they go down of n over d to the L. So let's say that this is the level 1. So I'm doing some sort of logarithmic scale here.
Andrea, sorry to interrupt, just a quick question about kappa. Why doesn't it scale like the L plus first eigenvalue? Because you took some sort of trace somewhere? I'm like a little confused why that term could possibly dominate, when you have the identity there. I mean, I understand it's proportional to the identity. I'm just asking about,
Well, this is, okay, so what I'm doing here is that I'm taking, so what is this is that I'm taking all the contribution of the kernel from, okay, so let's open a window. So this is really,
it's like a partial trace of your kernel.
No, I'm just, so this is what is k bigger than n, bigger than L, n is just k bigger than L xi xj, right? ij less than n. Okay, so this is what. Now I can decompose it into the diagonal and the out of diagonal, and the diagonal looks this.
I think Notability froze again.
Yeah, we can't quite see what you're writing the last like 30 seconds or something.
Oh, sorry. Thank you for letting me know. Okay, so I was saying just I'm decomposing the kernel matrix in, decomposing the kernel. Okay, perhaps I'll write down here. Sorry. So there was lambda times pj, okay, times whatever. How do I want to write it? Okay, perhaps I'll write it like this. Let's see if this works. And then there is what? Yjx1, Yjx2, plus sum over j L plus 1 to infinity of okay, so now I'm decomposing this into, so this is the part less than L, and this is the part bigger than L. Now I claim the following. So now the matrix bigger than n, perhaps I should switch to my usual blue. The part bigger than L of the kernel matrix is just the evaluation of the kernel, the part bigger than L, the kernel at the data points. Okay, and okay, so now I can decompose this into a diagonal matrix. The diagonal matrix is just all of these entries are equal. So let me call it kappa identity plus delta, where kappa is defined as the kernel component bigger than L, XX.
Yeah, but
Okay.
shouldn't kappa depend on L? Isn't it like the sum?
Yeah,
of
yeah.
n
Kappa
J's?
depend on the L.
But you wrote that it's order 1, right?
But
That's
L
what I
is
was asking about.
L is a fixed number.
Oh, we're fixed. Oh, I see. You don't care about the dependence on L.
Right. And I say that for any fixed L, this is a order 1. And the reason why it's of order 1 is that this is basically, approximately the following. If you follow the connection with the Hermite polynomial, is approximately the following. Take the part bigger than L of, you remember that K is an inner product kernel, H x1 x2 divided by D. Take the part bigger than L. So H can be analogously decomposed, right? So H can be written as H smaller than L plus H bigger than L, where this is the decomposition in the Hermite decomposition.
Mm-hmm.
In other words, bigger than L means projecting orthogonal to degree L polynomials in L2 of the Gaussian measure. Okay, and okay, so you have for a minute, trust me that decomposing it into Gegenbauer polynomials on the sphere is very similar to decomposing into Hermite polynomials for the real line. So this is the same as this. So this is H bigger than L1, and this is a number of order independent of the dimension.
I see. Okay, so the dimension drops out somehow. Great.
Yeah. So one other way to think, okay, this is not really a proof, but because okay, one can construct a proof like this, but it's it's more complicated. But if you want a heuristic, this is also good. This goes like d to the minus j. Okay, but on the other hand, so if you look at it, sum over j equal L plus 1 to infinity lambda square j times y jx. Okay, you will say, okay, this seems to go to 0 with the dimension, right? Because this log goes like d to the minus j.
Right, but then you're saying
on the other hand, this is exactly equal to BDJ.
Yeah, I see.
Okay, because
okay, yeah, thanks. Yeah,
it's expectation. The expectation of the integral of this is just the dimension of the eigenspace.
Yeah, exactly. Okay, I get it. Thank you.
Okay. Okay, so I was drawing this picture of the eigenvalues. It's really a log scale picture, if I think about it. The eigenvalues, there is the one of degree L that are basically of order n, then the other of order n over d, etc., up to n2 over. This is not the eigenvalues; it's the eigenvalues minus kappa. Now, kappa is of order 1, so it doesn't matter. And then all the other eigenvalues are basically kappa, right? So the first L eigenvalue are order n. I should have written here dj, sorry. So this is psi j over d to the j. Okay, so the first L eigenvalues are much larger than order 1, and then all the other values stick here, and they are equal to kappa. Okay, so in other words, this matrix is basically the identity, very close to identity, plus a multiple of the identity, plus very large eigenvalues that are low rank, that correspond to low rank components. So this is the structure. Now, what is the statistical interpretation? If you think about it, this is really a high sampled statistical interpretation. You have to look also at eigenfunctions. So these are the polynomials of degree j sampled on a very fine grid, and you have very large signal there. So what it means that you'll be able to fit very well low degree polynomials. Okay, so the fact that the kernel contains a low rank component that has a large eigenvalue means that the kernel is representing very well low degree polynomials, and so this is what we see in our theorem. And the fact that there is this piece proportional to the identity, this acts like a ridge regularizer. Okay, so the fact that you add the kernel as a piece proportional to the identity is basically implies is like shifting up by k the regularization. If you remember, the function that I'm fitting has the form the function that I learn has the form what lambda I plus k inverse, if I remember correctly, and then y. And if I substitute here in this guy what I had, so there is lambda I plus kappa I plus, if I something of the form lambda psi. Okay, so this is the polynomial basis, and this is just lambda plus kappa I. Okay. So this is the same matrix, the same regression matrix that you would obtain if you were doing a ridge regression with a slightly larger regularization parameter, so increased exactly by kappa, and you were just doing the regression, polynomial regression, so regressing with respect to degree L polynomials. Okay, so this explains this part of the thing, and okay, as Boris mentioned, I mean, when you look at the other limit case in which you only look at infinite sample size but finite width, you will see that what matters now is another kernel matrix, that is the kernel matrix of the neurons. Okay, this is at least in the random feature model. And so you see that now the kernel matrix, this is the matrix of, scalar product of the neurons with respect to the population distribution of the data, and you can construct a similar decomposition for this. Okay, when you have to keep into account finite neurons and finite number of neurons and finite number of data, now you have to look at a more complicated matrix, that is this whole matrix that is not a symmetric matrix, and you need to do a similar decomposition, but now it's not symmetric, so slightly more painful. Okay, I think I'll stop here. Check.
Great, thank you very much for the very nice lecture. In fact, I think this is the final lecture in your course, so maybe before questions, we can take a moment to thank you for preparing such nice lectures for us. I think everybody appreciates it. And I don't know if you have a couple minutes, but there might be some questions.
Yeah, I have a few minutes. There is not.
Oh, maybe that was just a accidental hand raise. I'm not sure. Oh, okay, maybe Siddharth has a question.
There is one question from.
Maybe this is a trivial question, but
Siddharth.
I missed the part why the diagonal elements greater than L part, they're all the same. The cup.
Well, they are all the same in this case because of just the spherical symmetry, right? Basically, the diagonal, so the matrix itself. I mean, the integral, the kernel itself is an inner product. kernel, and I'm assuming that I'm on the sphere, so xi are equal to in norm of square root of d. So the diagonal elements of the kernel here are equal to h of 1. It's a constant, right? Now, if you do the projection, what you have to convince yourself. So if you remember, I wrote, let's look at, so I decomposed as k less than L plus k bigger than L. Okay, of course, if I prove that the diagonal element of less than L are all equal, then by subtraction, all bigger than L are equal. So let's look at k less than L. And one way I wrote it is this is sum over j 0 to L. And then there are some eigenvalues, lambda j of d. And then there is the projection onto spherical the spherical harmonics of degree j, spherical harmonics of degree j. And now you can check that if you rotate the spherical harmonics, this is invariant, right? Because, okay, I don't know how much representation theory, but one way you see it is that the spherical harmonic carry an irreducible representation of rotations, right? So if I rotate J, if I act with an orthogonal matrix here, I act with the QJR YJX. Okay, so this is one way where Q is an orthogonal representation of. Perhaps there is an easier way to see this, but this implies in particular that the scalar product is invariant. And actually, as we saw before, since it's invariant, must be equal to the dimension of the space. It's the trace of the projector on 2 degree J polynomial. So this is the dimension of the space. Okay, there is a couple of other questions. Perhaps Romil.
Hello, Professor. Can you hear me?
Hi. Sure.
Yeah. So my question is not directly related to this talk. I had a question specific to like double descent. So like what we had been seeing so far is that over parameterizing has been giving us like better results despite what the classical information says and rather classical knowledge says, and we are looking at the different aspects of it, right? In between, there was a phase in machine learning where lasso had been introduced, or like using L1 norm as for regularization had been considered. So, and what we've seen is whenever we are looking at the over parameterized regime, we are always looking at the L2 norm. So, can you shed some light on how do the two compare, and like are there any specific benefits of maybe using L2 over L1 or something along those lines?
So first of all, I mean, the point is that, okay, so the phenomenon of overparameterization and overparameterization doesn't hurt. It has to do more that with what type of regularization you put, with how much regularization you put, right? As we saw, there is some regularization that you put. The point is that you put the regularization parameter going to 0 or much smaller than what you would expect classically, right? And despite things, these things work fine. Now, we studied here in the context of L2 regularization, but there has been work confirming similar phenomena for other regularizers. There are, for instance, some paper by Sarah van de Geer doing this with L1 regularization. And there is other people that did it in the proportional regime. There is a paper by Pragya Sur and Tengyuan Liang doing for boosting, that is L1 regularization with linear classifier and linear classification problems. There is papers, I think there is papers by Christos Stambropoulos doing also. Of course, when you go to L1, knowledge is not as precise or as complete as. And we have also a paper looking at other random feature models with other regularizations, right? So we have a paper with Michael Celentano and Theodor Misiakiewicz in which we look at, basically we don't look at statistical properties, more optimization properties. What we try to do some override, interpolation. So you minimize sum over I 1, 2, and let's say of let's say AI to the P, subject to sum over I 1 to N AI sigma of WI times X J equal YJ for every J, where the W are random. So this is a random feature models where you put LP regularization, right? So there is some work there, and kind of, you get similar phenomenon as for L2, but is kind of more difficult. The math is of course more difficult. Now, how does this fit with more classical? More classical is not classical, but a few years ago type of results on the loss, etc. I think that really the connection is what you assume about, on one hand, the structure of the signal and the regime of SNR. If you remember this figure that I showed you, this is a simple case in which you see the two things living together, right? Depending on, at the high SNR, it's okay to put regularization going to 0. Mm-hmm. At low SNR, you should put some positive regularization, right? And so I would say, but somehow even a positive regularization is not so bad at high SNR. So I think that this is kind of the picture, right? That at high SNR, it's okay to not regularize, but in some stuff like in vision or robotics, these kind of applications, but in genomics or biomedical applications, etc., probably you're working with very noisy data, and it's better to assume a strong structure because there is so much noise that otherwise you swallow by the noise. This is my picture of the two.
So, just adding to it. So, as you said that if we require a more stronger or rigid structure, we sort of have a positive regularizing parameter, right? So, in such scenarios, as you said that, there are similar results for over parameterization obtained for different regularizations. So, there is no proper comparison between these various regularizations as such, right? As in comparing using L1 with L2 with random features or something like that. Like, we are not able to compare them. It's just a part of it.
But you see, the point is that what doesn't, from a theory standpoint, is not really clear how would you do such a comparison, because it's obvious that if you assume that the truth is sparse,
yes,
it depends on your function, right? If you want to learn any polynomial of degree L, then but if you assume that the truth of sparse, and there are bounds on the Rademacher complexity, and but it's true. For instance, in the random feature models, there is not a lot of results about the generalization error of sparse random feature models, right? So that is something that has not been studied. So, as I mentioned, we have a result here, but even that is not that complete. And our result here, we study this kind of problem, and we ask the question of basically how quickly the limit, you can write a corresponding infinite width limit problem, and you can ask, okay, how quickly is the infinite width limit reached? And we show that it's sufficient to take n to be bigger than sample size to a certain power, right?
Yeah.
And this power depends on p. If this is bigger then you are really approximating the infinite width limit. But even this exponent, dependence on the exponent of p is not tight in our paper, so there is a lot of to be understood. There is not a statistical analysis, etc. Okay, perhaps move to. I'm not sure I can see the names. Don't see the name. There was a question from, okay, whoever is raising the hand. I don't see the names on the screen.
Yeah, maybe I just, it's basically a follow-up. Maybe you entered this already. So is it clear that the kernel regime, or this linear regime, is reached in the proportional case? Like when you have a neural network and you're in the proportional.
What do you mean by proportional? The two.
So when n, d, and capital N are proportional.
Right. Is it clear that it's reached there? I mean, there is this trick by Shizar and Bach that allows also always to get in the proportional regime, no matter.
By using
first of all, what you expect really is, for instance, for two-layer network, that the best that you can do is you expect rather this to be the important regime, right?
Right.
Because so now it can be shown that, or we show, and other people show that when you are, if you add here some log factors, then basically what happens is that the minimum singular value. Remember that one thing that matters for the kernel regime is the minimum singular value of the Jacobian
Right.
So you can prove that this is bounded away from the constant, right?
Okay.
Now, this is not sufficient, because if you remember, you have also to bound the Lipschitz constant, and the whole argument that I stated is not exactly tight. So the best result here, now I don't remember anymore, is that you need ND to be bigger than N squared, something like that. I think this is a result by Sametto, Imak, and Marisultan Oktabi. Now, all of this depends on what is the scaling of the normalization in front of the network. So, these statements are under this scaling.
Yeah.
There is this paper of Shizar-Bach that says, okay, if I take alpha large enough, as soon as you have this, then you're fine. So if I take alpha large enough, yeah, it's true that in the proportional regime, modulo log factors, then proportional, right proportional, meaning number of parameters over number of samples, then you reach the kernel thing, right?
Yeah, all right, that
okay,
makes
so
sense.
now there is a gray area that we don't know, right?
Okay.
But this trick of alpha allows me to tell you that all of the statistical results that I'm giving are concerned a non-empty set of.
Right. I mean, I was asking really, when you have a practical. Obvious.
Okay, you're breaking.
I guess to make sense that you can.
Okay, there is a couple of more questions.
Hey, I was wondering, so in your lectures, we've seen like a lot of two-layer networks. We've seen like lower bounds where the two-layer network's kernel regression like meets the lower bound. I'm just kind of wondering at a high level, do you see any role in this sort of context for studying deeper networks, or do you think, or what, I don't know, what do you think in general, but like, do we need to look at other models, other optimization dynamics, mean field techniques? You know, I'm sort of rattling it off, but I just wonder what your thoughts about that issue are in this context.
You mean about the kind of theory that I've been talking about, or?
Yeah, so I think from your
Other
theorems,
approaches.
it's clear in the kernel regression or the KRR setting that it doesn't matter if you use a deeper network, right? I think you've made that claim.
Right. I mean, if it is a deeper network that is fully connected, right?
Right.
But
sure.
now, if you look at what people use in practice, they rarely use more than 2 fully connected layers, right? They use a lot of convolutional layers. And now, if you look at convolutional layers, now 2 layers versus 3 layers, the kernel changes. And even for simple 2 layers, we don't have even an analysis of generalization in the kernel regime. Again, we have this paper that I briefly mentioned that I showed you the figure from, and then there has been a few follow-up papers. There is a paper by, I think, Joan Bruna, and there is another paper by I don't know whom. They study this kernel with convolutional structure. But yeah, I would say that is not yet a very well explored area, in particular, what is the role of architecture, etc. So the point is that this linear theory is in some aspect simplistic, right? Obviously, but on the other hand, it's something that you can do computations with, right? Quite detailed computations require some work. So there is one big open question in my mind in this deep learning is try to provide a way to match applications to architecture, right? Or provide any guidance, right? And so in that respect, I think the linear theory can be useful, right? So you want to probably construct an architecture that at least in the linear regime is good, right, for that application, right? So it would be very interesting to understand, okay, can you show an improvement when you pass from 2 to 3 layers or from 1 to 2 layers convolution?
Hey, Andrea, I had a question about, it sort of piggybacks off of what Boris was talking about in terms of expanding this to like a manifold setting. I was wondering how, like, I guess like when in the setup of the problem, you said that the WIs, they are distributed on the sphere. If I'm not, or it was either on the sphere or on like it's Gaussian, like you sample them, like they're random, but then they become fixed throughout the analysis, right?
Sorry, I got this. So the feature, sorry, I received a message from my wife. So you said the thing priorities. the xi are uniform on the sphere.
The WIs.
Yeah, yeah, the features, right?
The
weights.
Yeah, the weights are they're also on the sphere, or is that necessary for the analysis, or?
Yeah, so if I mentioned that we have this longer paper with a general theory, and that longer paper assumes an even more general random feature model, assume the following. So you have a feature model where, okay, let me enlarge this a little bit, where fxa is really 1 over n sum over I, or 1 over n, doesn't matter. So this is, now x is has some probability distribution on a space calligraphic x, and theta I have some other distribution mu on a space omega. Okay, and it's completely abstract. The 2 spaces can be any Polish spaces, so it can be infinite dimensional spaces. Now, this is a little bit hiding the difficulty, because then there is a certain number of assumptions that we have to make, right? And the assumptions are, I mentioned, for instance, that the diagonal elements of the kernel must be well behaved, and of course you must be able to say something about control the spectrum of the kernel or diagonalize the kernel. Now that becomes more difficult, right? So the short story is that you can push this theory to other distribution, but you must be able to make computations. For instance, when you compute the kernel, when you compute this kernel, you must be able to diagonalize this kernel, or to approximately diagonalize, to say something about the eigenvalues and eigenfunctions of this kernel.
The reason I bring this up is I was the pre-reading book that the high dimensional probability one that you just suggested that we read. I think the last chapter went over the Dvoretzky Millman theorem, which is like, if you take random projections with like random Gaussian matrices, then the convex hull is like in like sort of a sphere in probability. So it seems like if you can take your statements and just like shift them to be like in probability, if you are sampling from a manifold, then it might be like, and if the WIs are coming from a normal distribution, the thing I don't remember if it works out well is like, if you can somehow decompose like a Gaussian matrix into two, like so that you would still have some sense of weights, but you can sort of assume that the X's might have come from a manifold and then they get projected into like a sphere in probability. So like then it would because I was wondering which parts of like being on the sphere are you actually making use of, and it seemed from the things that you talked about, it's like it's the diagonal entries, right? So like they become constant and more or less.
Yeah, so the diagonal entries becomes constant, and then it helps to be able to diagonalize, right? Because if this comes from a sphere, I mean, there is also the measure on X, right? Now, if I have another measure on X, now, if I look at this as an integral operator, it's not clear how to diagonalize. Right?
Gotcha. Yeah.
But yeah. As I mentioned, something that has a certain degrees of symmetries. Symmetries help you in diagonalize operators, right? So if you have an object, a kernel that has a certain degree of symmetry, then that helps you do the calculation. So there was another question by.
Hi, I have a follow-up question.
Sure.
It's along the same line as Sam's question. It's more qualitative. So it's at a certain point, I expect the field to move on from linear theory like that. There's a bit of lack of satisfaction that kernels can't explain certain behaviors that neural networks are doing. What are some of the directions that you think that are possible, and what are the current roadblocks? Maybe it's technical. There's just certain things that we can't resolve mathematically.
Okay, so yeah, it's a good question. Yeah, the point is that in my mind, it's not clear how to. Let's see, what are the roadblocks? The point is that you would like some kind of theory that is both, that captures the nonlinear regime, but is predictive. I mean, there is a lot of work trying to, you look at one phenomenon, right? And then you show that is not explained by linear theory. And then you construct an example that captures that phenomenon, and then you prove a theorem about that example, right? Yeah, I mean, that's interesting each time. But it's not, in a sense, it's not very cumulative, right? So that is a little bit the frustration, right? So we did this work, before working on this linear theory, we did this work on the mean field limit. That is another way of looking at very large networks and try to get some limit behavior. I think it's an interesting direction to push forward. It has been pushed forward in some ways because there were generalization to multi-layers. There were all sorts of interesting results there. The point is that it's still, once you get to this mean field theory, the mean field theory is still very difficult to work with, right? So yeah, I mean, I think that these sparse random feature models are in interesting directions because they are non-linear and they, typically that it's going to be a tautology, but the things that I think are interesting are the things that I work on. I try to work there, it goes the causality direction goes the other way around. I try to work on things that I consider interesting, right? But yeah, I don't know. I mean, there is the whole question of what is the implicit bias, and but that question seems to be, I don't know if there is any possible, I mean, I don't know what is the end game of that question, right? And then there is another interesting direction is the optimization direction. Try to understand how overparameterization leads to tractability beyond the linear regime. Right? That's an interesting question.
So just to clarify a little bit, would you say that one of the difficulties right now is we currently don't really have a good framing of what is the mathematical question that needs to be solved?
No, I think that there start to be some good framings, right? I mean, there's some good questions. I think, for instance, why tractability leads to generalization. That why tractability leads to both why tractability, both the optimization question, that is why overparameterization leads to tractability, and the generalization question. I mean, I think there are three main questions, right? One is optimization. Why overparameterization leads to tractability. One is generalization. How comes you generalize despite interpolation and despite overparameterization? And the third is the architecture's question. How do you map one to the other? So for the linear method, within the linear regime, we basically have a pretty good idea of 1 and 2. So it could be interesting to attack 3, right? But beyond the linear regime, we don't have a real good understanding, I think, of 1 and 2, except, again, examples, I think. Yeah, so that is my hunch. So now, yeah, of course, we don't have the model. I mean, the point is that, like in many applied domains, once you have the right model, then it's a bimodal distribution. Either the answer comes very quickly or will never come. Or it is on the time scales of pure mathematics, right? So will come in 20 years from now, or 50 years from now, or a few centuries, right? So
that's satisfied with that answer. Thank you.
Having the right hypothesis is basically amounts to solving the problem. So there is one more question from Frederick. I think he has a raised hand. I don't know if that's it.
Yeah, so this question goes back to your lecture on Friday. There you mentioned that you had this linear model plus noise, and then you could compare this to the to the nonlinear model, right?
Yeah.
And I was wondering, is that something general, or I think there was something similar mentioned in like Jeff Pennington gave a talk that mentioned something similar from like the random matrix point of view. Is that?
Yeah, I mean, so if you look at these curves, so this is one case in which this can be proved, right? So basically, so this is in the linear regime, and these were curves are test error curves computed with respect to the nonlinear model, the random feature model, right? So now it turns out that the same curves are obtained by if you do this substitution and you replace sigma, so you can. So this is your design matrix, right? Phi. Now you could do the following things: replace phi. So first of all, I do an expansion. Each of these entries is approximately normal 0, 1 under my distribution of the. So I do the decomposition to sigma of t into, let me call it, okay, sigma naught plus sigma 1t plus sigma bigger or equivalent to t, where this is the projection in L2 of normal 0, 1 orthogonal to the first two, okay? In particular, sigma bigger or equal than 2 g expectation is 0, where G is a Gaussian random matrix, right? So if I now look at this matrix, I can write phi ij as sigma naught plus sigma 1 wi xj plus sigma, let's call it zij. And these Zij are uncorrelated from the rest. So Zij is xjwi. And now turns out, and this is, for instance, one thing that we prove in that paper, is that if I replace phi by this other matrix, where these are normal with mean 0 and the correct variance, sigma is not a good name, let's call it C, where C is chosen to match the second moment, then if you replace this by that, and if you replace the risks are the same asymptotically. Okay, so this is an equivalent random feature models, and this now you can analyze. You can analyze its behavior, applying just the theorem that I stated on Friday. Okay? In fact, this is exactly the latent feature model. Basically, is exactly the latent feature model that I discussed on Friday. Okay.
Okay. So,
yeah. So this is this correspondence has been proved, in this case, and then under some assumption for other convex losses. There is a paper by Chen, by Yulu at Harvard that proved, under some other convex losses, etc. But okay, I mean, it seems to be even more general than that.
Okay, thanks.
Okay, I guess that's all. So.
Okay, well, thanks again, Andrea. Yeah.
Thanks, everybody.
Bye, everybody. Don't forget there are TA sessions in principle if you are interested. Otherwise, see you all tomorrow, hopefully.
Okay.